All right, the first reaction of alkene is called hydrohalogenations. By the way, so all reactions of alkenes are called addition reaction, which means adding something onto the double bond. All right. So the first reaction we're also adding, so hydrohalogenation. What are we adding, by the way? Hydro, that's hydrogen, and halogen. There's the word halogen in there. Basically, we are adding a hydrogen and a halogen onto the double bond. Okay, and this reaction was found in 1869, long back there when a field of chemistry was still young. Vladimir Makarnikov, I know only his last name, that's how to say it. Makarnikov, he's a Russian chemist, right? He studied a bunch of alkene reaction, especially the hydrohalogenations, right? And this is what he found. When he adds halogens, not halogen, hydro, and what is it? An acid, hydrochloric acid, hydrobromic acid, hydroiodic acid onto an alkene. He found that X will go to the carbon in the middle, the one that have the more substitute carbon, and the hydrogen go to the other one. Look like right here, right? This carbon right here are more substitute than the other one, so X go to this one. Does not observe the other way around. All right. So, for example, propylene react with hydrochloric acid. He found that chlorine goes in there in the middle. This carbon is more substitute than the carbon on the right. We're adding this guy onto alkene. Not talking about this carbon, just these two alkene, two carbons. Right. The more substitute carbon got the chlorine. Right. You get that product, not the other way around. Adding this guys to, adding hydrochloric acid to this guy. Again, chlorine goes to the carbon in the middle, the more substitute carbon, and not the other way around. Can you guess if I have this compound adding hydrobromic acid, which carbon top and the bottom does bromine goes? The more substitute carbon, the top one right here. You get that? All right. So, and he summarized or come up with his rule. He's called Makarnikov's rule, in saying that hydrogen from like HX right here adds onto the carbon of the double bond having greater number of hydrogen. Here's what I mean. These two carbon right here, one of them have more hydrogen than the other. This guy right here, more hydrogen here. So 2 hydrogen, 1 hydrogen. 2 hydrogen, no hydrogen. 1 hydrogen, no hydrogen. Yeah. So the hydrogen of hydrohalic acid is going to go right here. Right, and the chlorine, bromine, the halogen gonna go onto the other carbon. That was his rule. Okay, and why though? How come though? Let's talk about the mechanism. That's the reason behind it. He didn't know at the time, but right now it is 2021. We know everything already. All right, what's going on? So we have a nucleophile. There's a double bond. Right, attack an electrophilic center of hydrochloric acid, which is the proton, the hydrogen. Attack. All right, let's say if this carbon right down here, so CS2 right here, gets this hydrogen, right, from bond with this hydrogen, that will leave carbon in the middle, become a carbocation. You have seen carbocation before, you know it's not stable, but tertiary is more stable than secondary and primary. All right, and then so we have the new nucleophile that's from the chloride coming out, and this your electrophile attack. Look at it like an SN1, but it's not SN1 anyway. You get this compound. Now, another possibility, instead of this carbon gets the hydrogen, what about carbon in the middle gets that hydrogen? That's possible too, like that. You get a carbocation right here, and then chloride attack. Can you tell which reaction is better in terms of like more stable? Gonna be the top one right here. Tertiary versus primary. Primary carbocation can't even exist. It's really unstable. All right. So this guy is more stable. So its transition state is more stable or lower in energy. So less activation energy basically. So lower activation energy, the reaction go much more faster. All right. So that's why we don't chlorine never goes to the less substitute carbon. Chlorine, bromine, iodine always go to the more substitute carbon because it passed through more stable carbocation. That's the reason behind it. Okay, so the product that has halogen on more substitute carbon is called Markovnikov product, and the other way around we call anti-Markovnikov product. All right, so this reaction favor Markovnikov product. We don't really observe anti-Markovnikov product there. Okay. All right. If you look at the energy diagram, like kind of repeat what I just see earlier, there are two ways that happen. You get carbocation in the middle or carbocation on the right, right? And you can see that if you get carbocation in the middle, the tertiary one, the activation energy of the transition state is much lower than the primary. So the reaction go here much faster, right, to get the other product. Okay. All right, let's talk about the stereochemistry of it.